All right. Just go ahead and get started. So the homework assignment this week is uh, a little bit on the last chapter. The first two problems are on momentum and collisions, and then the last 8 problems are on rotation. So we can start off obviously with just sort of doing them in order here. But the first two problems are going to be probably the most difficult. So yeah, these are like the the 3 dot level problems from the momentum chapter. This is just how the class happens to line up as far as the order that the material is covered. Um, so the first chapter, or I'm sorry, the first question has to do with collisions again. This is a bullet fired into a block problem, and the reason that I refer to it with a name like that is because this is a very common problem. Um, a bullet is shot into a block, it passes through the block, or it becomes embedded in the block. If it passes through the block, then you have the momentum of the bullet and the momentum of the block before and after the collision. If it becomes embedded, then you have a single mass with a single momentum afterward. So in this problem, this is a little, I guess you could say, like an, an even more difficult variation of that problem because there are 2 blocks and 2 collisions. So the first collision, the bullet flies through the first block. So you have the initial and final momentum of both the bullet and the block. And then the second collision, the bullet is going to become embedded in the block. Now, the problem that you have to do requires you to work backwards, starting from the second block. So starting from block number 2, what happens here is you have a bullet that's flying into the block, which is at rest on the ground, and the bullet is going to become embedded. So we know that if I sum up my momentum initial and my momentum final, or in other words, before and after the collision, then this momentum has to be conserved. I will note that the energy is not conserved here. But in our initial picture, we have the mass of the bullet, which we'll say is BU, times the velocity of the bullet initially. And then we have plus the mass of the block, BL, times the velocity of the block, BL. And now, since this is the second block, the bullet becomes embedded in the second block. And that means that you'll have a single mass traveling at a single velocity. So that the momentum final will be the mass of the bullet and the block times the velocity of the bullet and the block after the bullet becomes embedded. So what are our knowns here? What are our unknowns? They give us the final velocity of the block and the bullet together. That would be your V2. So that'll go right in here. Oops. And link those two together. The mass of the bullet and the block takes a little bit of work on your part. And in order to do that, you need to add together the mass of block 2 and the mass of the bullet. So you do the mass of the bullet plus the mass of block 2. Initially, we have that let's start with the block itself. Both blocks in this case, but we're just concerned with the second one. But both blocks start at rest. So that means that your initial momentum for block 2 is going to be 0, and so you'd only have the mass of the bullet times its initial velocity. Now, the only unknown here then is the initial velocity of the bullet. To plug in the stuff that we have, the mass of the bullet in my problem is 3.5 grams. Make sure to convert that to kilograms. So that would be 0.0035. We have that times the velocity of the bullet initially. Our second term here was 0. So this will just be equal to the sum of the mass of the bullet and the block. So my bullet has a mass of 0.0035, and then the mass of block 2 for my problem happens to be 1.78 kilograms. And then we will be given the speed of the combined bullet block system. In my problem, that's 1.35. Okay, so I'd solve here, and I only have one unknown, so I just need to isolate. And if I do that, I'm gonna write this off to the side. I would get the speed for the bullet initially is going to be, for me, it's 688 meters per second. So let's talk about what that velocity is. That is the speed that that the bullet comes into block 2 with. So that's our speed right here, is 688 meters per second. Now, since we're working backwards in this problem, this is the speed of the bullet after it leaves block 1 and before it makes contact with block 2. So this 688 that I find here will be, yeah, okay, that's correct. This will be, the first solution. And then I need to carry this over to the second part of the problem. So for the second part of the problem, I want to find the bullet when this block enters, the speed of the bullet before it enters block 1. So the second part of the problem, working backwards, is now we have block 1, and we have our bullet is going to fly, hit block 1, and then it's actually going to travel through block 1, and it travels through and ends up with that 688 meters per second that we just found. So for this problem, it'll be very similar to what we did in the last page, where we're going to sum up our initial momentums and set it equal to the sum of our final momentums. Initially, we have the mass of the bullet times the velocity of the bullet initial. Again, we have the mass of the block times the velocity of the block. Again, this block is at rest, so you can write it out if you'd like, but this is also going to be 0 because this block starts at rest. Now, when we do the final momentums, in this case, the bullet does not become embedded in the block. Since the bullet does not become embedded, it means that both the bullet and the block will have a momentum final. So we have the mass of the bullet times the velocity of the bullet final plus the mass of the block times the velocity of the block final. All right, and the block will gain some speed, so its final momentum is not going to be 0. It will have some momentum. We can go ahead and plug in our mass for the bullet. We know is 0.0035. We don't know the incoming speed. That's actually what we're looking for. So go ahead and leave that as V bullet initial. We set this equal to mass of the bullet again is 0.0035. And the velocity of the bullet final, this is where our answer from the first collision with the second block comes in. So it's 688. And then we have plus the mass of block 1 and its final velocity. Those are both given in the problem. For me, it happens to be 1.28, and the speed is 0.63. Again, we have just one unknown. We just need to go ahead and isolate it. And this will be the velocity of the bullet initial. And the velocity of the bullet initial for me happens to be 918 meters per second. Notice that these are in the range of several hundred meters per second. That makes sense for speed for a bullet. Okay, so yeah, you should definitely be comfortable with doing bullet hitting a block problem. It's a common collision type problem that you'll see. It's a good quiz problem, although the quiz this week is only on rotation, and I've been authorized to say that you're only concerned with the rotation portion, but it's definitely a good exam problem. Okay, problem number 2, we have two blocks colliding. And the actual collision here shouldn't be too difficult, although there is a part that asks about change in kinetic energy. Why do we talk about a change in kinetic energy? Isn't energy always conserved? Well, keep in mind that we know that momentum is conserved always, but energy doesn't necessarily have to be conserved. So I have two blocks. I have one block that's traveling and collides with a second block. And my first block has a mass of 3 kilograms, and it is traveling for me with 3.9 meters per second squared. I'm sorry, just meters per second. And it's going to collide with a 6 kilogram block that has a speed of 2.6 meters per second in the same direction. So we have two blocks, each have mass, each are going to have a speed, so they both have momentum initially. Now, after the collision, the second block is going to move away with a speed of 3.3 meters per second. So you could draw another diagram if you'd like, but I'll just go ahead and label on here that the V final for this guy is going to be, what did I say, 3.3 meters per second. So initially it was traveling at 2.6, this block bumps into it, and now it's going to increase its speed. And we are asked about, first of all, the velocity of the first block, and then we're asked about the change in the kinetic energy. So in order to find the velocity, we know our momentums have to be conserved. So sum up your momentum initial, and that'll be equal to the sum of your momentums final. Go ahead and call these block 1 and block 2. We have m1 v1 initial plus m2 v2 initial has to be equal to m1 v1 final plus m2 v2 final. Okay, so we're given most of the information that we need here. It's just a matter of plugging it in. Mass 1 is 3. The initial speed of block 1 is 3.9 plus mass 2 is 6. The initial speed of block 2 is 2.6. This is equal to mass 1 again is 3. We don't know V1 final. That's what we're going to solve for. Mass 2 is again 6, and the final speed is 3.3. Solve here. You could probably take a guess that if block 2 speeds up, block 1 will slow down. For my given values, that gives us a V1 final of 2.5 meters per second. And yeah, cool. Okay, so we have the speed here, and I can go ahead and put that on my diagram up here, that this V final is going to be 2.5. And so that calculation is pretty straightforward. Now, the second part of the problem asks about the change in the kinetic energy. So that maybe is the difficulty for this problem. I'm going to go ahead and reuse the same page. In order to find, of course, the change in the kinetic energy, I just need to calculate the kinetic energy before and after, and then subtract them. So if you'd like, you could do kinetic energy initial and kinetic energy final. I think I'll go ahead and do it that way. So my initial kinetic energy will just be the kinetic energy for the first block initial plus the kinetic energy for the second block initial, which will be 1/2 m1 v1 initial squared plus 1/2 m2 v2 initial squared. And again, I know my initial speeds and I know my masses, so it's just as simple as plugging in. This will be 1/2 times mass 1 is 3. Velocity for block 1 initial is 3.9 squared plus 1/2 mass of block 2 is 6. And the speed of block 2 initially is 2.6. I square that. And you go ahead and solve, go ahead and plug this into your calculator, and you'll get a kinetic energy initial. Repeat this calculation to find the kinetic energy final. And then your change in kinetic energy will be K final minus K initial. If you need any help with that, let me know. But I think that calculation will be pretty straightforward. And then the last part, they give you a different final speed for block 2. So you just repeat these 2 steps and change this from 3.3 to whatever your other speed is that's given. Okay. So I'll give a second in case anyone has any questions. This is the end of the momentum chapter. So we're going to go ahead and move into rotation. I don't hear anyone chiming in. So before I get into the actual rotation problem, I'm just going to sort of do an overview for what's going on in this chapter. So we dealt a little bit with rotation with centripetal acceleration and centripetal forces. But for the most part in this class, we've just been dealing with linear motion. So what happens in the rotation chapter is we want to develop a more robust system for looking at rotating objects. So what that means actually for our class is that we're just going to take all the things that we know. One sec. The question asked was, wouldn't the kinetic energy be zero with the masses and velocities? No, because your kinetic energies are going to change. So when we have a collision, the kinetic energy will change. This is the calculation for the initial kinetic energy right here. When you calculate the final kinetic energy using these speeds instead of these ones, then you'll get a, oh, you didn't square the velocities. Okay, cool. All right. So yeah, so as I was saying, my pitch here is that when we are looking at the motion of a rotating object, which initially we're just going to do like a single position or a single point mass that's rotating, the idea is just going to be to take the things that we already know and just redefine them in terms of rotational aspects. So what I mean is we had position initially, X, Y, or Z, or R, just represents a spatial position. Now when we're dealing with an object that's going around in a circle, instead of being concerned with its location on the X or Y, or X and Y, now we'll be concerned with its location along that circle, which is given as an angle theta. So if I move this way to some point here, I have some angle theta. The way that I translate between X and theta, or between any position in theta, is that it's the arc length, S equals R theta. And that's how you turn the distance around the edge of a circle into some angle theta. Okay, this one maybe is a little bit less helpful, that actual equation. But this idea of translating from position to angular position can be repeated. So we know that we have speed or velocity. We want to turn that into an angular velocity, omega. And this omega represents how fast the object is rotating. The translation here is that V is equal to R omega. This is a translation that you will make. And the last one is we have acceleration. Acceleration becomes angular acceleration, alpha. And the relationship there is that our linear acceleration, A, is equal to R alpha. The way that you can remember where the R goes is that the units on these, the units for theta is radians, the units for omega is radians per second, and the units for alpha is radians per second squared. A radian is a unitless measure. So by multiplying, for instance, radians per second by meters, we end up with meters per second. Cool. So this also means that all of the relationships between between position, velocity, and acceleration that we had linearly will carry over. So remember, if I wanted to get from position to velocity when I was doing linear motion, I would do a time-based derivative, right? So that's going to be the same relationship here, time-based derivative. If I wanted to get from, say, acceleration to velocity or from velocity to position, then I would integrate with respect to time. Same thing will happen here. If I want to get from alpha to omega, I integrate with respect to time. And the idea here is that we don't need to change our physical understanding or physical processes. Everything that we've already been using will still apply. So one big example are the kinematics equations. So just to give one example, one kinematic equation that we've used a ton is delta x is equal to v initial t plus 1/2 at squared. We already know this equation. We don't need to learn a new equation. All we need to know is that we just need to translate each of these variables. So delta x, what's that going to become? Well, remember, we're going to turn our x, or positions, into angles theta. So this will be delta theta. Our initial velocity, we know that velocity v, the linear velocity, is now going to be in omega. So we literally just substitute in omega initial times t. And then plus 1/2 our acceleration. What's our new acceleration? Now it's this alpha guy, which is just the rotational acceleration. Cool. So we just go ahead and do 1/2 alpha t squared. So you can do this. I've done it with one equation. You can do this with all the kinematics equations as long as you know to replace position with theta, v with omega, and a with alpha. You don't need to learn anything new. You can just do those substitutions. This will work with basically everything that we've done, energy, momentum, all that stuff. The one thing that I will note is that when we deal with rotational masses, we cannot simply replace mass with some rotational thing. Okay, so this will not work. There's no correlation. Well, there is a correlation, and we're going to talk about it at the end of this chapter, but we're going to set it aside for now. But what we can do in the meantime is we can talk about just motion up until we introduced forces and things like that. So there's my speech. Let's go ahead and talk about one of the problems. So problem number 3, we're given an angular position function. And I'm just going to sort of write down a simplified version here. Theta is equal to 4t minus 3t squared plus 6t cubed. I have a function for theta, which is a position. I have a function for position in terms of time. We've done problems where we have functions of position in terms of time, and historically we've ended up taking some derivatives, right? So in this problem, they ask us, first of all, what are the angular velocities? Well, I know angular velocity is omega, and I know that velocity is still going to be related to position by a derivative. So my omega is going to be the derivative of theta. Just go ahead and take your derivative. Derivative of 4t is 4. Derivative of negative 3t squared is going to be minus 6t. Derivative of 6t cubed will be plus 18t squared. And that's it. We already know how to do that. We just take a derivative. Now we have an omega function. They ask you to evaluate it at 2 times. I'm going to bet that everyone has a good handle on how to do that. They then ask us about the average angular acceleration for a given time. And the average acceleration, well, first of all, angular acceleration itself would come from a derivative. But if I want just average acceleration, remember that the average acceleration is, let's start off, let's just talk about it in terms of linear quantities. So if I wanted to find just an average linear acceleration, I would do just delta v over delta t. So if I want to find an average angular acceleration alpha, then instead of delta v, I'll do delta omega over delta t. And I have my omega function here. So when I go to do delta omega, which is just omega final minus omega initial over t final minus t initial, I just evaluate the function at the 2 times that are given, and then I can find the average angular acceleration. And then finally they ask us about the instantaneous angular acceleration. The instantaneous angular acceleration will be the actual acceleration function. And again, we've already done acceleration from a velocity function. Remember, it's just the derivative of the velocity. So we just take a derivative of our angular velocity. Derivative of 4 is 0, minus 6t is minus 6, plus 18t squared will be plus 36t. And that's it. There's your acceleration function. And then they just ask you to evaluate at the 2 times given for the interval. Okay, problem number 4. So this was just a calculus problem. Problem number 4 is where we'll actually do a little bit of kinematics. We have a drum. The drum is going to rotate around its central axis. We're given an angular velocity, and then we're told that it's going to slow at a given rate. So for kinematics, we had acceleration, initial velocity, final velocity, delta x, and time. To translate these to the angular quantities now, we'll have alpha, omega initial, omega final, delta theta, and time. That's it. We're just using different variables. Now it's simply a matter of doing the kinematics problems that we've already done 100 times and that we know how to do. So our drum is rotating at an angular velocity of 11.1 radians per second. That would be your initial omega of 11.1. Drum's going to slow at a constant rate. Since it is slowing, that means that our acceleration is negative, and mine happens to be negative 8.74. We're asked how much time. Oh, it's going to slow at this rate. And then, yeah, and then we're asked how much time it takes and how far it travels to come to rest. So our omega final is going to be 0. And then essentially we just have 2 different problems, and the 2 problems are going to, the 2 parts of the problem are going to ask us to find delta theta and to find t. So let's just try finding delta theta. All right, I need the equation that has alpha, omega initial, omega final, and delta theta. Maybe that doesn't immediately ring a bell, so you can go back to your linear equations and say, all right, I need the equation that has acceleration, initial, final velocity, and displacement. I know that that equation was v final squared equals v initial squared plus 2a delta x. And then I can say, all right, let me just translate this to the angular quantities. So this will be omega final squared is equal to omega initial squared plus 2 alpha delta theta. That's a very hideous theta. There we go. All right, nice. And then this equation is going to work the same way as it did when we were doing linear motion. Omega final here is going to be 0. So I have 0 squared is equal to omega initial squared, which is 11.1 squared, plus 2 times my alpha, which was negative 8.74, times my unknown delta theta. Notice I have only the unknown delta theta, so I can isolate it, and this will give me 7.05. And then as far as what the units are, keep in mind instead of meters, we just turned meters into radians. So meters becomes radians, meters per second becomes radians per second, and meters per second squared becomes radians per second squared. So this is just 7.5 radians. One thing that I'm going to mention right now, I'll leave the other part of the problem, finding the time, up to you. I think you've got a grasp on how to do these, hopefully. One thing that I will mention is that not a lot of people, someone is going to mess up because they're going to look at this and say, okay, we're dealing with radians now, right? I need to turn my calculator into radian mode. Keep in mind, your calculator only needs radian mode when you're doing sine, cosine, and tangent. And off the top of my head, I cannot think of an instance where you're going to actually be plugging in like sine of delta theta or something like that. So do not worry about switching to radian mode in this class. Stick to degree mode. Don't ever go to radian mode. All right. Problem number 5 is going to be a similar kinematic problem. Let's look at how we go through it. We have a merry-go-round rotating from rest with a given angular velocity. I want to know how long it takes to rotate through these two different revolutions. Now, one thing that I will note is that they give us revolutions as a unit, and we haven't talked about revolutions, so just as a real quick sort of what that unit means. A revolution is one time around a circle. So it is a measurement of an angular distance, but we know that we want our angular distance in radians, right? So how many radians are in one circle? You already know this from pre-calc. It's going to be 2 pi radians. So when they ask me, in my problem, they ask about 4.67 revolutions. I need to convert that to radians, and I know that there are 2 pi radians in one revolution. Okay, your revolutions cancel, and you end up with, what is that, 9 point, I don't really, that's 9.33? Is that how 0.67 plus 0.67 works? I feel like I made that up. 9.33 pi. And I would just recommend keeping your pi as you're doing the homework problems. Yeah, you'd probably also just keep 4.67 times 2 pi and just keep that in there until you go to the calculator work. Okay, so for the problem itself, again, we're doing kinematics, acceleration, initial velocity, final velocity, delta x in time becomes alpha, omega initial, omega final, delta theta in time. My alpha is given as 1.67, I'm sorry, 1 minus 1.68, whatever, everyone's different. My omega initial, if I am starting from rest for the first part, my omega initial will be 0. I don't know omega final. I do know my delta theta will be 4.67 times 2 pi for my 4.67 revolutions, and I don't know time. So you're actually going to need to do two problems here. The first problem is to find the actual answer. In that case, you need to find your t. For the second part, in order to do part B of the problem, you will need to find your omega final and then use that as your initial omega for the second 4.67 revolutions. There's another way to get to the answer for the second part. There's a little bit of a shortcut, but I wouldn't recommend trying too hard to shortcut when you have a direct way of doing the problem, even if it's a little bit longer. Okay, so let's just do one of them. Let's do the one where we want to do find the time. So we have alpha, omega initial, delta theta, and time. Remember, that's acceleration, initial velocity, delta x in time. So that equation was delta x is equal to v initial t plus 1/2 at squared. That's the equation that I know. Just go ahead and translate your quantities. That'll be delta theta is equal to omega initial times time plus 1/2 acceleration times time squared, 1/2 alpha. All right, so my delta theta is 4.67 times 2 pi. My omega initial is 0, so this first term is 0, plus 1/2 times my alpha of 1.68 times t squared. Notice t is the only unknown here. Be careful with your calculator work. For my values here, my time would be 5.91 seconds. All right, so that's one kinematics problem. As I mentioned, you'll have to do a second kinematics problem to find omega final, and then you'll use that omega final as an omega initial and repeat this calculation to find the time for part B. Okay, problem number 6. Problem number 6, upping the difficulty just a little bit, we have two wheels, and there is a belt around the two wheels. So some motor here that's being driven by this belt, and our two wheels are going to rotate around their centers, and the belt's going to go around. Now, as this belt is going around, since the belt links the two things together, like on a bicycle, the bicycle chain is going to move at a constant linear velocity. And this is the hint that they give you in the problem, that the linear speeds at the rims are going to be the same. And I'm going to change the direction because I want to be doing this in terms of positive rotation always. So what do I mean when my linear speed's the same? That means that my v here is the same as my v here. Now I know that these two disks are not going to rotate at the same speed. This is like the entire basis of a bicycle, right? Is that I can crank the front thing with the pedals, and when I spin on the pedals, I am inputting a certain amount of what's called torque, which we'll get to next week. But I'm inputting a torque, but because of the different sizes of the gears on my bicycle, I generate more drive on the back half. And that's because of again, the different radii. So go ahead and call these disks, say disk 1 and disk 2. And I know that the linear speed or the tangential speed will be the same for both. So V1 will be equal to V2. Now they give me the radii of each, and they give me the angular speed of wheel A. Actually, they give me an angular acceleration there, radians per second squared. They say it increases from rest, and they ask how long it's going to take the other wheel. Oh, they actually have names. They're not 1 and 2. They're called A and C for some reason. The belt is called B. Um, okay, so call these A and C. And yeah, so I'll go ahead and change this as well. Call these A and C. Okay, yeah, so they give us some information about A. They give us the speed of A, starts from rest. They give us the angular acceleration. They ask for the time for speed C to reach a certain angular speed final. Notice they give that in revolutions per minute, so we need to convert that to radians per second. Yeah, so the first part will be to link the two speeds together. And in order to do that, we can consider this relationship here. The speed of A will be equal to the linear speed of A will be equal to the linear speed of C. And to go back to our, oh, is it still here? Yeah. So the way that I converted from linear speed to rotational speed was with this equation right here, that V is equal to R omega. The two speeds are equal because there is a belt linking them together. So they actually tell you kind of explicitly in the problem to treat them as if they are, it's the hint at the end of the problem. The belt does not slip, the linear speeds are the same. So V sub A is equal to V sub C. And as I just mentioned there, that means that if you do R sub A times omega sub A, that'll be equal to R sub C times omega sub C. So this is how we can take the rotational information about A and translate it into rotational information about C. Further, we can also say that the tangential accelerations would be the same. So that means that the acceleration at A, tangential acceleration will be equal to the tangential acceleration of C. And to turn this into angular quantities, this is R sub A alpha sub A is equal to R sub C alpha sub C. And this is the basis, this relationship is the basis by which I can take the information that wheel A has, so alpha sub A, and my problem is like 2 radians per second squared. And since I'm asked to find the time to reach a final speed for C, well, I can relate that to the radii of the two disks and find the alpha sub C. So alpha sub C solving this guy would be r sub a on r sub c times alpha sub a. So whatever angular acceleration they give you, plug that in here, plug in the 2 radii, and you'll have an acceleration for c. So I'll leave that up to you. Once you do that, then it just turns into a kinematics problem. So the kinematics problem will have our alpha, omega initial, omega final, delta theta, and time. The alpha will come from that r sub, what did it end up being? R sub a on r sub c times alpha sub a. Our omega initial, since we start from rest, is going to be 0. Our omega final is 120 revolutions per minute. The way we convert from revolutions per minute to radians per second, we have to multiply the revolutions by 2 pi, and we have to multiply the minutes by 60. So you'd multiply by 2 pi on 60, or pi on 30. And then we don't care about delta theta, we're just asked to find the time. So we just pick the equation that has acceleration, initial final velocity, and time. Remember that was v final equals v initial plus at, which is now omega final is equal to omega initial plus alpha t. Okay, I'll leave the rest of that problem up to you. Problem number 7. For problem number 7, we have a graph that we are asked to read, which is fine. I think we can read the graph. We don't need to do a derivative or anything. We don't need to find slope. But one thing that I will mention is that this problem is asking about rotational kinetic energy. So I suppose this is the time to introduce the concept I promised, which is how we translate mass to rotation. So let me take a step back here and just talk about mass that is undergoing rotation. The example that I always use is my pen. If you hold your pen at the middle and you rotate it, it takes a certain amount of effort. If you hold your pen at the end and try to rotate it, hopefully you can notice that it takes a little bit more effort to rotate your pen about the end than it does about the middle. Why does it take more effort? It's because of the distribution of the mass. When I'm holding my pen at the middle, I have half the mass that is located half the length of the pen to the left and half the length of the pen to the right, okay? When I hold at the end, I have some mass of my pen that is the entire pen length away from my fingers. So by holding in the middle, all of the mass is within half the pen's length of my fingers. When I hold at the end, I have mass that is up to a pen length away. So that very hand-wavy explanation hopefully will clue you into the fact that we have to consider not only how massive the object is, but how far the mass is from the axis of rotation, which in this case, in the pen example, the axis of rotation is set by my fingers. And oh man, dropped it. Changed the problem, but we're good. Okay. So yes, so we have to do a little bit more work. It's not just as simple as translating mass into inertia, but let's go ahead and talk about it. So we have mass that we are just generally going to translate into this thing called rotational inertia. And the rotational inertia will always account for the distance from the axis of rotation. There's always going to be some sort of calculation in there where you have a particle that is some distance from the axis of rotation. If you do have a particle, then the way that you'll get from mass to inertia is you'll do I is equal to mr squared, and that will give you an inertia. And r in this case would be the distance from the particle to the axis of rotation. So if I were doing something like this, where I have, let's say I wanted to rotate a particle about the origin, and my particle was located over at x equals 2, then what is my distance from the origin or my axis of rotation to the particle? That would be a distance of 2. And so I'd plug that in for my r, and then I'd multiply that by the mass. So this is the way that we convert our mass into some angular mass, is that we have to multiply the mass by the square of its distance from the axis of rotation. Okay, so that's for a point particle, which they'll give you a lot of problems with point particles because that's more a little more straightforward. We can also deal with uniformly distributed masses. So for instance, my pen is a rod, and there's essentially just a table of inertias that's in your textbook that you shouldn't be responsible for memorizing. But there's a table for a whole bunch of different shapes of masses, and all of them have been derived from the inertia equation. In general, the general definition of the rotational inertia is that the rotational inertia is the sum over all the particles for the mass of the particles m sub I times the position of the particles r sub I squared. This is your general definition. And for those of you who are quick with the calculus, you'll know that any sigma, any sum can be turned into an integral to generalize. And so someone has already done all the integrals for you. You don't need to be responsible for the integrals, but that's where that table for all the different spheres and stuff comes from. Okay, so we're going to do a problem with rotational inertia in a second, but I needed to emphasize that mass and rotational inertia kind of stands alone. For this problem, however, we're not going to have to do, for problem number 7, we're not going to have to do anything with the rotational inertia directly, but it's about to show up in an equation. So we're asked about kinetic energy. We know that kinetic energy was 1/2 mv squared. And if we want to find a rotational kinetic energy, then just as we've done so far in this chapter, we just need to replace our linear quantities with our rotational quantities. So we have 1/2. Our mass now becomes rotational inertia I, and our velocity v becomes angular velocity omega. So there we go. We have kinetic energy 1/2 I omega squared. And for this problem, they're going to, for part, let's see. For part A, actually, you do need to find a slope because they ask you about the angular acceleration. We know that in angular acceleration, here, let me just sketch out this graph. The graph looks something like this. Okay. And it is a plot of omega versus time. So for part A, if I want to find alpha, I know that alpha is the time derivative of omega. So that would just be the slope of this graph. That'll be your alpha. For part B, they give you a specific time and a specific rotational kinetic energy. And I'm assuming that those will be the same for everyone, so you can read a nice even 4 off of the time. So at 4 on the graph, what you'll see is that your omega is also 4. And so they'll say at t equals 4 seconds, you'll have a kinetic energy of, say, 6 point, whatever, it probably doesn't matter a whole bunch what it is. Let's just say it's 6 joules. And then I will read off the graph and I'll say, okay, at 4 seconds, I know that my omega is 4. So I'm supplying that information myself from the graph. Why do I care about this information? Because if I know my kinetic energy and I know my omega, I can use this equation to solve for my rotational inertia. So with this equation in tow, we'd have a kinetic energy of 6 is equal to 1/2 I times my omega of 4 squared. And that will give me a rotational inertia of 0.75. This isn't your answer to the problem. This is just the rotational inertia. The units of rotational inertia, since it's mass times distance squared, will be kilogram times meter squared. This inertia will be constant for this object. So when they ask us to investigate the kinetic energy at time t equals 0, that will be down here on the graph. And you'll just read off the omega here, which is -2. And then you'll just calculate, again, using k equals 1/2 I omega squared. you'll use your omega of -2, and you'll use whichever inertia you found from this calculation here. Okay, so we didn't have to actually directly calculate the inertia on this problem, but on the next one we will. Oh, let me clear out some of these whiteboards. Okay, so in problem number 8, we have an arrangement of disks that are located, there's 15 of them. I am going to do less than that. I'm gonna do 5, how about that? And they do keep going out. So I will do the problem as if they're 15. I'm just not gonna draw 15 of them. There's a center, and these disks are gonna be rotated around the center. And we're told that the total length of this arrangement over the 15 disks has length L. And then they give us the mass, they give us that length, they give us the mass, and yeah, there you go. So first of all, one thing that I know that I'm going to need, since I have these disks, is I'm gonna need the radius. And I want the radius of each in terms of that length. So the length will cover 15 disks, and you notice that they're diameter to diameter. So that means that the length divided by 15 would give you the diameter of each. So the radius would be the length divided by 30, right? The diameter divided by 2. Okay, so set that aside. Now they asked me to just directly calculate the rotational inertia. And the first thing that I need to know is the rotational inertia for a solid disk. And I know from the table that is, actually, I'm looking at the table and I don't see it, but the rotational inertia for a solid disk, this is just kind of given to you. Rotational inertia for a solid disk is 1/2 mr squared. As I mentioned a few slides ago, that comes from doing an integral that you are not responsible for doing. Now this, I should mention, is actually they use capital R, so I will use that just for consistency when you're looking at the textbook. This is the rotational inertia for a solid disk about its center. So for the center disk, which is rotating about its center, this is its rotational inertia. However, if I'm rotating a solid disk like the one next to it around that center, I have to translate the rotational inertia by this length right here. How am I going to do that? This is a thing called the parallel axis theorem. The parallel axis theorem says that I around some parallel axis is equal to whatever I through the center is translated by a length mh squared, where h is the distance from the center of my object to the parallel axis that I want to rotate it around. So for instance, for this disk, the one that I've been highlighting, I know that its rotational inertia through its center is 1/2 mr squared. And then I need to add in m times the distance from the center of that disk to the actual axis that I am rotating around, which is 1 diameter or 2 r's away. Okay, so that might be a little heady. Just give it just a second to breathe. Now, I have 15 disks. One of them is rotated around the center. So for the center disk, 1/2 mr squared, cool. The other 14 all need to be translated. So I know that I have this guy, which is translated here, and I know that this disk would be translated the same way. So as I'm actually solving this problem directly, I would have 2 disks that have this inertia, and then I'd have 2 more which have 1/2 mr squared plus m times 4r squared. and then 2 more at 6, 8, and so on. So what am I going to end up with to generalize here? The inertia of the entire system. First of all, each one of these terms, notice, will have a half mr squared. So if I have 15 disks, I know that for each 15, I will have a 1/2 mr squared. So I can sort of shorthand factor that out, say I have 15 times a half mr squared. And then I need to translate my 14 other disks. So I just said I have 2 of them, which are translated by a distance m times 2r squared. And then the next 2 will be translated by a distance of 4r. So 2 times m times 4r squared, plus another 2, which will be a distance 6r, and maybe you'll start picking up on this pattern. 6r quantity squared. 1, 3, 5, 7, plus 2 times m times 8r squared. These are the guys that are 4 disks away. Plus 2 times m times 10r squared. 2, 4, 6, 8, 10, 11. Plus 2 times m times 12r quantity squared. Plus 2 times m, 2, 4, 6, 8, 10, 12 times, let's see, 14r squared. How many do I have now? 2, 4, 6, 8, 10, 12, 14, 15. Okay, cool. Yeah, so there you go. There's a very annoying problem to work with. You could probably reduce it if you want to. You could certainly factor out some 2's, factor out an m, absolutely. Factor out an r squared for sure, and then just sort of combine the terms there. I'll leave that up to you. The one thing that I will mention, the mass, so for this problem, yeah, so they have a total mass given. Wait, let me hold on, make sure I get this right. Then glue together into a rod with a given length and a given mass. Yeah, so the m here is the mass of each disk, and the mass of each disk would be your mass that is given divided over the 15 disks. Thank you for asking that question. Yeah, so I'll leave the grunt of that grunt work up to you. What I will mention is that they then ask us to approximate the arrangement as being a uniform rod of mass m and length L. And for that, you would use, excuse me, the uniform rod inertia. And so I'll give that to you. Of course, you can find it in your textbook. But that inertia for the rod that you'll need for part 2 is 1/12 mL squared. The other thing that I'll mention about this problem is just that this is obviously very laborious, and you're mostly not going to have to do this kind of long parallel axis theorem. It's unfortunate this is the only, I think, example problem that you have on the homework, and it happens to be so long. Usually the way you'll use it is you'll have like a sphere and you're rotating the sphere around its end. That's like a radius away. That will mostly come up next week when we deal with torques. Just to give you a sort of look ahead, torques is how we translate forces to rotation. So forces translate to rotation is its whole own thing and deserves an entire chapter to itself. Okay, problem number 9. Yeah, okay. Yeah, Nina, I can do that if you want to stick around. Okay, so problem number 9, maybe would have been a better one to start with. Problem number 9 is 4 point particles. We're given the mass of each and the position of each, and we are asked to find the rotational inertias about a set of axes. So I'm going to go ahead and place these 4 particles in the XY plane. So I have a 29 gram particle. You'll notice, first of all, units are given in grams and centimeters, and you can calculate in grams and centimeters. I know I say always convert your units. This is one case, one problem where you don't need to convert your units. So we have a 29 gram particle located up here. And then I have a 19 gram particle located at x equals 0, y equals 8. So that'll be somewhere up here. And then I have a 31 gram particle at -6, -6, which will be somewhere down here. And then I have a 37 gram particle at -4, 8. That one is, what did I say? 37. Okay. So you have XY coordinates for each of these. They'll be different for everyone, I believe. Yeah, so we're gonna do rotational inertia about each of the 3 different axes. So the first axis that they give us is the x-axis. So the x-axis runs right here. Now, in general, when I need to find the rotational inertia of the system, the rotational inertia will be the sum of the mi/ri squared. To demathify that equation a little bit, I just have to do m times r squared for each individual particle. What that means is that, for example, for my 29 gram particle, I just need the distance from the 29 gram particle to the x-axis. You take your shortest straight line distance. So since my 29 gram particle is located at 4, 4, this is just 4 centimeters. And when I go to calculate the mr squared for that particle, the mr squared will just be 29 times 4 squared. For my 31 gram particle down here in the third quadrant, that guy was located at -6, -6. What is the straightest short line distance? That's just 6 centimeters. And so when I go to calculate the inertia for that one, it'll be just 31 times 6 squared. And then both of these guys are a distance for me of 8 centimeters. So I just take their masses, multiply by 8 centimeters squared. And then once I've calculated this for each of the 4, I just add them together, and that will give me my inertia. So leave that up to you. That's for the x. For the y, then you're just going to measure the shortest straight line distance to the y-axis. Whoops. Which would just be from this particle over to the y-axis would be your the second part. I'll go ahead and talk a little bit about the third part, where we need to find the distances around the inertias, rather, about the z-axis. Our z-axis passes through the origin, oh no, and points out of the page. So when I'm calculating the inertias for each of these particles, about the z-axis for part C, I need to take this distance as the shortest distance. So for instance, my 29 gram particle that I've just drawn the line to, that is located at 4, 4. So the r that I will plug in here for the z-axis calculation, that r will be the square root of 4 squared plus 4 squared. What would the units be? So in general, my units for inertia, since it's mass times distance squared, are kilograms meters squared. For this problem, since we're doing grams and centimeters, it'll be grams centimeters squared. Okay, I think I spent enough time on this problem. Just make sure that, that you do the quadrature distance from the origin for the third part. Yeah, okay. Problem number 10 then is going to be in a similar vein. We have 4 particles that are placed on the edge of a square and connected by 4 massless rods. It just means that they're held in place. Since those rods are massless, we don't need to be concerned about the rotational inertia. Then we're going to ask to find the rotational inertia of this body about an axis, and they're going to stick the axis in different places. But the approach is going to be the same as it was to the problem that we just did. So first of all, we have our 4 particles, and they're on the edges of a square. So let's say that the square is 4 meters by 4 meters. So that would be, just to sort of generalize, this would be 4 meters by 4 meters, and they're each going to have the same mass. So we don't need to worry about that. Now they're going to give us 4 different axes. The first one passes through the midpoints of opposite sides and lies in the plane of the square. That would be an axis that passes through the midpoint of both sides and lies in the plane of the square. In order to calculate the inertia, the rotational inertia around this axis, remember I take the straightest short line distance from each particle to that axis. So this distance, which is 2 meters, this distance, which is 2 meters, this distance, which is 2 meters, and this distance, which is 2 meters. That's because it's just half the side length of the square. And when I go to do mr squared, it'll be the same r for each of them. It'll be r2, r is equal to 2. And you'll have just one inertia for each particle. So you'll just do mr squared, and you'll just sum from I equals 1 to 4, but it'll actually just become 4 times mr squared because they're all the same mass, the same distance from that axis. Okay, so that's for the first part. The second part, we want an axis that passes through the midpoint of one of the sides and is perpendicular to the plane of the square. So it's going to pass through the midpoint and it's going to be perpendicular to my page, which means it's going to be, say, over here. Now, when I go to calculate my mr squareds, I will have, first of all, the 2 particles that are located closest. No. That'll be this particle and this particle. Those are each located half of a side length away, so they're each 2 meters away. So I'll have 2 of them that are just m times 2 squared. Okay, that'll be pretty straightforward. For the other 2 particles, though, those 2 particles are located on this weird diagonal, and I need to find that length. I know that the side length of this guy is 4, and I know that half the side length is 2, and I know that this is a right triangle. So this distance would be the square root of 2 squared plus 4 squared from the Pythagorean theorem. All right, so when I go to do my sum of my mr squareds here, I'll have 2 of them. Sorry, I'm kind of bring this down here so I have room. I'll have 2 of them that are located at, that are mass m located at a distance of 2. And then I'll have 2 of them that are a mass m that are located at a distance square root of 2 squared plus 4 squared. So I have to square that too. Okay, and then the last one is we're going to lie in the plane of the square and pass through 2 diagonally opposite particles. This will be our last axis. And for this one, we're going to send it, instead of being perpendicular to the page, it'll be parallel to the page, like in the first part. And it's going to just pass through 2 opposite diagonals. I keep erasing. So that'll be something like that. All right, so let's talk about what's going on here. Again, from the symmetry, we only have 2 different types of particles, right? So we have the 2 particles that lie on the axis itself, and then we have the 2 that are some distance away. So first of all, to start with the guys that lie on the actual axis, when I go to calculate my mr squareds for those, what is the r from, say, this point to the axis? That would be an r of 0. So that would mean that I have an mr squared of 0. So what this means is that there is no rotational inertia for that particle because it exists as a single particle. If it exists on the axis of rotation, it doesn't contribute to the inertia at all. To sort of tie that into conceptually what's going on, remember that in order to make this pen difficult to spin, I needed to locate my mass some distance away. If I have mass that's all located on the axis of my fingers, then there's not even any rotation going on. So there's no rotational inertia. So this particle and this particle have no contribution to the rotational inertia. I then just need to calculate this straight line distance. And it's the same straight line distance for both of those particles that are off the axis. And it is 1/2 of the diagonal of the square. So my square is 4 meters by 4 meters, which means that the entire diagonal is 4√2. If I then just need the distance from one corner to the center, then that's just going to be 1/2 of my diagonal. So that'll just be 2√2. All right. So when I go to calculate the inertia of my 4 particles, again, I have 2 that have an inertia of 0 plus 2 that are a mass m located at a distance 2√2. So I have 2√2 quantity squared. Whew, all right, that is a long chapter. If you have any questions, you'd like to stick around, I can answer those questions. And I know, let me hit the stop recording here.